Hi, welcome back. This is our second type of product for vectors. This time the cross product is another vector. Okay, so let's figure out how it works and what it represents. Okay, so the cross product, and to evaluate it, we use what's called the determinant operation, which you may have seen already if you took linear algebra. So in particular, if you have this object, 3, 1, 2, 5, take the determinant of that thing, you're going to multiply 3 times 5, that will be 15, and then you subtract 2 times 1. 2, oops. So the determinant of that thing would be 13. Okay, okay. So let's try it with some vectors here. And with this, you have to have vectors in space, so you're not working in the plane anymore, because the result of the cross product will be a vector that's perpendicular to the given vectors, and that would go out of the plane. So anyways, let's say 12, negative 3, 0, and negative 2, 5, 0. So find the cross product, and we will write that u cross v, so it kind of looks like a multiplication. You're going to build this box here. Across the top, you're going to put I, j, k. And then you'll have 2 rows inside the box, one for each vector. Put the first guy in the first row. That's actually the second row, I guess. And the second guy in the last row. Okay, so we're basically going to have 3 determinant operations. And the first determinant operation is going to be this box here. Okay, so if you could see my hands, which you can't, maybe when I guess we're not going to be in class, but what I do is kind of cover up for the first component of the vector. I cover up this row and this column and find the determinant of the leftovers. Okay, so for the first component, it's going to be negative 3 times 0. Minus 5 times 0. Okay. And then the next component is always negative, so you're going to put a negative in front of there. And then let me erase this chunk. So I'm going to kind of cover up this column and this row and find the determinant of the box. That would be 12, negative 2, 0, 0. Okay, so the first term here in my second component would be 12 times 0, and then minus 0 times negative 2. Okay. Then the third component in my vector, so get rid of that and that, I'm covering up the first row and the last column and figuring out the determinant of this. Okay. So I'll have 12 times 5 minus negative 2 times negative 3, which of course is just 6. So let's just write 6. Okay, and then I do a little bit of arithmetic. So that first component is going to end up being 0. And then the second component is negative 0. And then the third component would be, what, 60 minus 6, so 54. Okay. And of course, in standard unit vector notation, you can write that as 54 ijk. If you wish. So that's pretty much the tall and short of it. Maybe we should do one more cross product just to make sure you have the hang of it. And let's see if they give us one in the book we can try here. Okay, sure. Well, actually, let's just do v cross u, right, and see what happens. See if this product is commutative, like the dot product. Is u cross v the same as v cross u? Okay, so that'd be mildly interesting. All right, so I, j, k, negative 2, 5, 0, 12, negative 3, 0. And I guess the book doesn't really put it in component form. They always use the standard unit vector notation, but I like component form better. So the first component, cover up that stuff. It will be 5 times 0, which is 0, minus negative 3 times 0, which is 0, comma, and then the second component's always negative. Let's go cover up this guy and this guy. So negative 2 times 0 is 0. Oops. And then 0 times 12 is 0. And then the third component. So I'm going to cover up first row and last column. I'll have negative 2 times negative 3 is 6. And then minus 5 times 12, which is 60. So I end up with 0, 0, negative 54. In other words, negative 54k. So it seems like it's almost commutative, but not really. U cross V is the negative of V cross U. And you'll see that in our properties of vectors. Okay? So Theorem 11.7 is going to give us a bunch of handy-duty little properties. 1.7. So the first one you see, the cross product, and this is the first time we've seen this happen, is not commutative. It's like everywhere in the world of math, it seems like everything is commutative, but it's not necessarily going to be true. And you probably already know that if you work with multiplication of matrices, right? Right. Then we have some distribution properties. So U cross V plus W. We can rewrite as U cross V plus U cross W, and all kinds of other neat stuff, right? Usually you'll just use these to simplify computations, or you'll use them in proofs. Let's look at another. If you take a cross product of a vector with itself, it's just going to equal the 0 vector. We could actually prove number 5. Proof of 5. PFF, I don't know why the PFF, but there it is. Okay, so let's let our vector U in space be described by the components U1, U2, U3, and then note from the way we've defined the cross product, U cross U is equal to I, J, K, and then U1, U2, U3, U1, U2, U3. Okay, so the first component of a cross product is going to be U2 times U3 minus U2 times U3, which is clearly going to be 0. And the second component, the cross product, is going to be U1 times negative U1 times U3 minus, again, U1 times U3. And, whoops, I put that in the wrong place. I meant to put it up here. U1, U3 minus U1, U3. Okay. And again, clearly that's 0. And the third component then, let's go ahead and do that, is going to be U1, U2 minus U1, U2, of course. That will also be 0. So that's the 0 vector, which is what we were trying to show. Therefore, the cross product of a vector with itself is equal to 0, just like it says in the theorem. Okay? Okay. Let's look at the geometric kind of properties. So when we talked about the dot product, we kind of talked about the dot product as a measure of alignment between two vectors. The way I see the cross product is more of a measure of orthogonality. So the more aligned they are, the lower the number. So you see if they're in the same direction, the cross product is 0. When they're completely out of alignment, that's when your magnitude of the cross product will be greatest. Okay, so anyways, it's kind of, you think of it as kind of a measurement of orthogonality. Okay, so theorem 11.8 gives us some of these geometric properties. And again, you'll use these in simplifying computations and proofs. And later on, we'll need to develop some sort of vector integrals. And when we're doing that, we're going to be integrating over top of rectangles and squares. And it turns out the area of this region demarked by these two vectors is the cross product. And you can find the area of that parallelogram just by taking the cross product of the vectors. Okay, so the first one to note is that the cross product of two vectors is orthogonal to the individual vectors. Okay, so it is perpendicular. No, let's say orthogonal, it's probably better. Okay. Secondly, there's this kind of relationship between the vector, the cross product, and the angle between the vectors, sort of, right? Before, the dot product was equal to the magnitude of the vectors times cosine theta. Now it's the magnitude of the cross product. So that wasn't in there before. And also, it's not cosine, it's sine. And I'm not going to prove this. But it's almost exactly like the dot product formula that we had in the previous section. If you find that the cross product is equal to the zero vector, that just implies that the two vectors are parallel, or they're the same, right? So that implies that u is parallel, or we could say u is a constant multiple of v. The area one, this will come up later in the class, probably towards the end of the class when we're talking about vector calculus and developing integrals of vectors and that sort of stuff. But anyways, the cross product of these two vectors is equal to the area of the parallelogram formed by the vectors. Okay, so that thing I was talking about here in the beginning, it's equal to the area of this parallelogram. Okay. So that will be useful. Also, we're not going to get into it, but the area of the parallelepiped, forgive me if I mispronounce that. The guy, my teacher was French, so he would have all kinds of weird pronunciations. So this is the volume of the parallelepiped, which is basically the kind of the parallelogram in 3 dimensions. So you might have something like this. I'm butchering the picture, but you get it's the area of that thing. Okay. Let's prove the fourth one, which turns out to be kind of important later on. So proof of 4. And we could get away with this using a bit of trig. So here is vector u on the bottom, and then vector v right here. There's some angle between them, and we want to know the area of this parallelogram. Okay. So the area of parallelogram, if you didn't know, is just base times the height. So we basically need this dimension right here. And we need this dimension right here. Because the area is going to be equal to base times height. Okay, so the base is no big deal, right? That's just going to be the magnitude of u. The height is this distance right here. So I'm going to have to use some trig to figure that out. Let's call this h, I guess. So, you know, what do we have here? It's the sine of theta is equal to opposite over hypotenuse. And of course, we want the magnitude of v. So h is going to equal the magnitude of v sine theta. So over here we have the base is the magnitude of u, so, and then the height is the magnitude of v sine theta. And then from the second theorem, I guess we could leech off that. We haven't proved it, but let's use it. That magnitude of the vectors times sine theta is equal to the magnitude of the cross product. Okay, so that's equal to the magnitude of u cross v. Not a very well-written proof there, I know. Please forgive me for, let's just call this a sketch of the proof, right? Otherwise, my teachers will be rolling in their graves. Okay. The typical problem you see in the homework, what are we going to be dealing with? It's just practice finding cross products, so find u cross v, and then they have this extra question on there, basically just show that the cross product is orthogonal to the individual vectors. So and show that it is orthogonal to both u and v. Okay. Okay, so let's look at an example. We use standard unit vector notation. So I have I plus j plus k, and then v is 2I plus j minus k. And let's find u cross v. Okay, so again, I, j, k. And I go 1, 1, 1, and then the other guy is 2, 1, negative 1. And then I just like using component notation. So first determinant is the 1, 1, 1, negative 1. So 1 times, I'll go ahead and do this. Okay, so 1 times negative 1 is negative 1. Minus 1 times 1, which is 1. The next component, you always put a negative in front of it. Do that. So now looking at that portion. 1 times negative 1 is negative 1, minus 2 times 1 is 2. And then the third component. We have 1 times 1, which is 1, minus 2 times 1, which is minus 2. So we're getting negative 2, negative 3, or 3, and then negative 1 as our cross product. Then we want to show that it's orthogonal to both u and v. So to do that, you just do a dot product. So u dotted with u cross v. And that will equal 1, 1, 1, dotted with negative 2, 3, negative 1. So 1 times negative 2 is negative 2. 1 times 3, and we're adding these together, sorry. 1 times 3 is 3. Negative 1 times 1. 1 times negative 1 is negative 1. So that equals 0. So yes, that works. And then the other way around, or the other vector, rather. So 2, 1, negative 1 dotted with 2, 3, negative 1. So that'll be negative 4 plus 3 plus 1, which again is 0. So that shows that both vectors are orthogonal to each other. Have any other? Yeah, so they have some geometry problems. I don't think there were any of those in the homework. But so what they want you to do is show that the given points create a parallelogram, and then they want you to find the area. So I guess we could look at this guy. It's example 3 in the book. You almost have to plot it at first in order to kind of get an idea of which sides are which, so you don't accidentally have like a cross, like you accidentally, you know. So you kind of need to almost graph it at first, figure out what's going where. So 1, 2, 3, 4, 5, and then 1, 2. So of course that's right there on the stupid axis. So that's A, B is 2, 6, 1, so 1, 2, 1, 2, 3, 4, 5, 6. 2, 6, and then 1 is B, and then let's see, C is 2, 4, 7, 1, 2, 1, 2, 3, 4, and then it's way up here somewhere. So C, and then D is 5, 0, 6, so 5, 0, and then it's way up here somewhere. So I think the picture A is connected to D. Yeah, they draw it there for you. So A is connected to D, D is connected to C, C is connected to B, and B is connected to A. What you want to show is that like AD is parallel to BC, or CB is the way they're doing it. Don't matter. CB. And then you want to show that AB is parallel to CD. Okay. So you need to get those vectors just by doing differences, basically, of the points. So A is 5, 2, 0. I guess I should write these down. And then 5, 0, 6. And then C is 2, 4, 7, and then B is 2, 6, 1. So AD is 0, negative 2, 6. CB is going to be 0, 2, negative 6. And you can see AD and CB are just constant multiples of each other, so they are in fact parallel. And then you get AB. So AB is going to be 2 minus 5 is negative 3, 6 minus 2 is 4, 1 minus 0 is 1. And then we need CD. 2 minus 5, negative 3, 4 minus 0 is 4, 7 minus 6, and those are exactly the same, so those are definitely parallel, so it's a parallelogram once we've established that. And then we need to find the area of the parallelogram. So to get the area, I would take like AB and AD and get their cross product. So AD cross AB. And let's do that. IJK. A little more practice doing cross products. AD is 0, negative 2, 6. AB is negative 3, 4, 1. Okay, so the first one, negative 2 times 1 is negative 2, minus 6 times 4 is 24. This component's always negative. Zero times 1 is 0. 6 times negative 3 is negative 18. It's minus negative 18. So it's really easy to make arithmetic mistakes when you're finding this cross product. After a while, you may want to just put it into like Wolfram and get the cross products there when you're doing your homework. You won't be able to do that on a test, but at least on your homework. Especially if you're doing tons of cross products like later in the semester. It's not going to let me. There we go. Okay. Last guy then. So 0 times 4 is 0. Minus negative 2 times negative 3 is positive 6, and minus 6. So this will be negative 26, negative 18, negative 6. And then we need the magnitude of that for the area of the parallelogram. If you're looking, yeah, okay, so AD cross AB equals the square root of that chunk, which is going to be huge. 18. Of course, if you square a negative, the negative will go away, so I'm not writing the negatives for that reason. And then go to your calculator. 26 squared plus 18 squared plus 6 squared is 1036. Take the square root of that. So I'm getting about 32.19. See if that's what they got. Yeah, okay, great. One of the applications then here with regards to physics would be torque. So basically you're taking the cross product of, so you're moving like a wrench or something like that. I have a picture. No? Yeah. So you're moving like a wrench, and you consider the wrench as being represented by a vector. So if you look at this picture, the vector would be PQ. And then the other vector is the force vector, is pressing on the wrench at a certain, in a certain direction. So you get a vector for that. And then if you take the cross product, that will give you the moment of the force about the this point P here. And then you can get the magnitude of it if that's what they want. So find the moment of the force about the point. Okay, so let's see if we can pull this one off. This is what example 4. Okay, so there's a vertical force of 50 pounds. So you could represent that vector just with 0, -50. And then we want a vector for the lever, so PQ, I guess we could call it. And they give you a length. And 1 foot. It's a 1 foot lever. Be careful, because some of the problems in the homework will give you the measure of the lever in terms of inches, and really you need it in terms. Let's see if they try to pull that junk on you here. Yep, no, they don't. Okay, they're not going to be jerks. Yeah, they are in this one. So it says 6 inches, but you're going to have to convert that into 1/2 of a foot. So you got to get everything in terms of the same. You know, because they want their answer in feet pounds, which is the units for torque. So you have to make sure that you're working not with 6 inches, but with 1/2 feet. Okay, you got to make sure all the units are good. Okay. So anyways, the lever vector, I guess you could call it, is going to be 1. The magnitude of it is 1, and then the angle is 60 degrees, so cosine 60, sine 60. And of course we could figure that out using our brains. We don't need a calculator. Cosine of 60 is 1/2, sine of 60 is √3/2. Okay. You know, technically there's not a third component. We could just assume it's 0. Maybe I should have went 0, 0, -50, just to be accurate with the picture. Okay. And then this other guy, let's assume it's in the YZ plane. So it's going to be 0, 0, and then those things, or 0 rather, cosine 60, sine 60, like that. Okay, and of course that's 0, then this is screwed up. 0, 1/2, and then √3/2. Okay. Okay, so let's get the cross product for the moment vector, and then we can get the magnitude of that, and that will give us the, and it's supposed to be, first you do the lever, and then you do the force. Okay, so this, 0, 1/2, √3/2. 50. Okay, so first deal, 1/2 times -50 is -25. And then -0, but 0 ultimately. And then 0 again. So looks like the magnitude is going to be 25 foot-pounds of torque. Clearly, if you do the magnitude of this moment vector, you see equal to the square root of -25 squared plus 0 plus 0, which is the square root of -25 squared, which would be 25 foot-pounds of, yeah, So yeah. Oops. Oh no, that's that. Yeah. Okay, we're good. I think that's about it. They'll have you experiment. This is just trying to help you build some intuition with cross products. Cross products. They do a little bit with the triple scalar product. That's not going to be important for us, so I'm just going to kind of leave that to you. If you want to get into it, you can read it. But I don't think there's any homework exercises on it, and there are not going to be any future work in that domain. That's not to say that you won't see it in your life. If you do some weird, if you go into some weird field, maybe you'll see it again. But for us, we're going to be okay without it. So I'll just leave it at that. I think you should be able to do the homework from that point. And so, as usual, thank you for watching, and I'll see you next time.